Good evening and welcome to Lowell Observatory and our celebration of astronomy on National Astronomy Day. My name is Kevin Schindler and I'm the historian here at Lowell Observatory. And joining me tonight is Lauren Biddle, one of our graduate research assistants here at Lowell Observatory. And we're coming live from the plate vault at Lowell Observatory. We're really in the bowels of the observatory. This is down below ground. Behind us are these old glass plates, photographic glass plates. And these ones in particular behind us are ones that were taken by Clyde Tombaugh and in his search for a planet that Percival Lowell called Planet X that led to the discovery of Pluto. So it's really neat to be sitting in here in this historic area because we're going to be talking to Lauren today about a lot of different things. But one of them is going to be, the technology that she uses today. So we don't do photographic glass plates anymore. It's changed a lot, how we do imaging and look at light from space and such. So it's kind of interesting to look at the evolution of how we collect light. So this is a special program tonight because we're celebrating astronomy. National Astronomy Day is a great time, to just take a moment away from the craziness of the world, from electronics, although we're looking at monitors here, but it's a great time to really just appreciate the sky. And sometime later tonight, go outside and take a look up and really, take a look at the stars and other things that are up there. It's a passion that so many people have. And for some people, they become so passionate about it that they decide to do this for their career. And Lauren is an example of this. Lauren is, if we do this program in another year, we'll be calling her Dr. Lauren or Dr. Biddle. I like Dr. Lauren better. That sounds like a cool ring there. Because she's working on her Ph.D. right now at Northern Arizona University while she collaborates with one of our astronomers, Dr. Lisa Prato. So Lauren, let's just talk because the goal of this tonight is to talk to somebody that's really passionate about astronomy and talk about how she got interested and the kind of work she does. With the understanding that while Lauren is really devoted to this, astronomy is really for everybody. And we all can look up in the sky and be excited about it. And that's how Lauren started out sometime years ago, just like so many of us. At some point, she looked up and got interested. So we'll talk about that a little bit later on. But first of all, let's talk about what you do here. You're a graduate research assistant. So what does that mean?
So being a graduate research assistant means that you receive funding for doing research to earn your PhD. And so I work with a research group here led by my advisor, Lisa Prato, and Joe Llama. And we are focused on stars and planets and disks being around young stars. And it's really been an amazing experience here.
And I mean, you're a graduate research assistant, and a lot of people might think that as a graduate student, you're certainly doing research, you're learning how to do research. Mm-hmm. But you're not only learning how to do it, you've done some fundamental things in searching for planets around other stars in terms of how to identify them, right? Mm-hmm. Can you talk about that a little bit?
Yeah, so identifying planets around stars can be easier or more difficult depending on the type of planet and the type of star. And so the type of stars that we are most interested in are extremely young. They're called T-Tauri stars. And these stars are only a few million years old. And that might seem like a lot, but if we were to compare the lifetime of a T-Tauri star to that of a human, then these stars would be like in the first week of their life. And so there's a lot going on here. They've got a lot of magnetic activity, and they've got disks where the planets are forming around these stars. And so finding planets in those disks can be difficult. So it requires some creativity to figure out how exactly we do that. And one of the ways that I've learned that we can do that, my team and I actually developed this method of detecting planets around young stars with disks, in that the planet will interact with the disk. And we can see that in the form of brightness changes of the system over time, and brightness changes of the system over time by accretion. And what accretion is material from the disk traveling along magnetic field lines onto the surface of the star. And that basically creates a huge explosion on the surface of the star. And that's what we're looking for, because the planet will pulse that material down onto the star. So really what we're detecting is evidence that a planet is there, but not the planet itself. And so because of that, it requires additional observations to confirm their existence. But this is one way that we can flag it up and say, oh, there might be a planet around this kind of star.
One of the reasons we decided to operate from this room, of course, is this represents a search for a planet that started more than 100 years ago and culminated in 1930. And you think about the techniques, the same thing. They were guesstimating where to look based on the irregular movements of Uranus and Neptune. Percival Lowell, starting in 1905, started predicting, based on how these are moving, there should be a planet located in a certain place, a certain size. And so a lot of the same, different techniques, and yet the same idea of inferring what's out there. And there's a lot more to the Pluto story, that this planet they were looking for that was really big isn't there. They just happen to find little Pluto right there. But that's part of the excitement of doing science, is sometimes you look for something specifically, other times you find it, sometimes you don't, sometimes you just happen on something, and it's just part of the process of really doing it, and doing it systematically and well.
Definitely, yeah.
So we've come a long ways in planetary searches.
Absolutely. Yeah.
How did you get interested in doing this? Were you always interested in looking for planets, or as you become a graduate student, did you have a professor that inspired you, or how did that get going?
I've always been curious about how we got here. And so that question was the driving force behind my interest in exoplanets, because I would love to find other systems that look like our own, that could potentially host life just like us. And so that was mainly the driving force.
And it's somehow perfect that you're at Lowell Observatory. You've been here since 2015, in a place where Percival Lowell, the founder, was inspired to study Mars, with the idea, are we alone? That's why he started this observatory. And you're continuing that mindset 125 plus years later. So it's a really neat tradition, although the techniques you're using are a little bit more advanced than what we were doing back then. So how did you get us interested in astronomy in the first place?
So I've always been curious about the world around me. When I was very young, I remember asking a lot of questions. And at one point, I think I was really frustrated that there weren't a lot of answers to the questions that I had. And so I asked my parents one year for Christmas for a book of answers. Mm-hmm. I just wanted to know. Unfortunately, no such book exists. No book has all the answers to everything ever. But that stuck with me, just the curiosity. Mm-hmm. And so when I was very young, my papa, who's my grandfather on my mom's side, he gifted me a telescope. And my grandparents spent a lot of time in Florida. And we looked at a lunar eclipse one night through this telescope on the beach. And it was such a magical moment, because there was very low light pollution there at the time. And so the stars in the sky were it was stunning. And that got me interested in astronomy at a very young age. And then it wasn't until I was in high school that I knew that I wanted to do this as a profession. And I have my high school teacher, Mr. Pinnell, to thank for that. He had an astronomy class that gave us the opportunity to do astrophotography. Mm-hmm. And we actually did this with film, with like old school film cameras. And I think they do it digitally now, but it really just the details that go into capturing a beautiful image really, I think, grabbed me. And then I was like, yep, this is it. This is what I'm going to do. And so, yeah, it's kind of like a shorter version of my journey.
Well, that's excellent. And I was going to ask a follow-up, but we also have a question from David Moore. And it's a good reminder that if you have questions while you're watching for Lauren about her research, how she got interested in astronomy, anything like that, write them in and we'll try to get to them. But David asked several questions. What made you choose this specific part of astronomy when there's so many different things? And also which telescopes are you using, because he lives not far from the Lowell Discovery Telescope.
Mm-hmm. So what made me choose this planets was just the curiosity about how we got here. And then the telescopes that I use, I do use the Lowell Discovery Telescope. And I've also been using lately telescopes in space. There's the Kepler telescope that is currently doing the K2 mission, which is the follow-up mission to the NASA Kepler mission. And then I've also used data from TESS. And so what this allows is we don't have to take breaks for daytime. We can just observe certain parts of the sky for all time. We don't, well, not necessarily all time, I guess. Like for TESS, it's like 30 days in a row without any breaks, really. We can take data. And then for the K2 mission, which is done now, we could stare at a single part of the sky for like 80 days, I think is what it was. And the Kepler mission before that, it was like 4 years straight. And that was so important for discovering planets around other stars, because we could detect more transits that way. And so what a transit is when the planet passes in front of the star in our line of sight, it will create a dip in the brightness of the star. And it does that periodically as the planet orbits. And so the longer we can stare at the piece of the sky where stars are, the more likely we are to catch planets that are transiting further out from their star, because it takes longer to come around and have full orbits. So that was incredible for the advancement of this area of my science.
Yeah. So there are several techniques for finding planets around other stars. And over the last several years, the number of known planets has skyrocketed. Yeah. Is there an estimate of the percentage of stars that have planets? An estimate of what that would be?
So there have been studies done for different types of stars. And I don't remember the specific numbers right now, but it is very likely that when you look at a star, it probably has a planet.
Yeah.
And it also depends on, there's current research being done on whether binary systems can have planets, or like what the statistics are on those. Because even though the majority of stars that we look at are not necessarily in multiple star systems, there are enough stars in each multiple star system that if we look at all stars, most of them are actually in binary, in tertiary, and even quadruple star systems. And so multiplicity is one thing that's being taken into account currently. And so even as we know it, the current rate of planets around stars might change depending on our findings.
It's really fascinating to think about, just fundamentally, if you're in a system that has multiple stars, you would have multiple sunrises and sunsets. And also, what's the length of time that a planet could last with those? I mean, the amount of time that there's regular orbiting with the gravity of two different stars, does it ever get to where it's stable, or does eventually it get, tugged apart or something like that? There's a lot to learn about it.
Absolutely. Yeah.
And so for you, the ultimate thing would be to find life somewhere.
Oh, yes, that's the dream.
So what keeps you going on a daily basis? Do you think about that every day, or is it, I mean, there's still the excitement of like the new method you help develop or develops in searching for them. I mean, what keeps you going on a regular basis? Because we'll talk about this in a couple of minutes, but a typical day for you is probably a lot of staring at a computer screen. And somewhere along the way, you kind of get tired of that probably.
The eyes do.
Yeah. So
Yeah.
what keeps you going on a daily basis?
It really is the wonder that I have for are we alone or not? And although I may not be right now looking at planets that are likely to host life, remember these planets are extremely young. So they're probably, they're still forming. So they're not very suitable to host life right now. But those planets might someday be. And then that can help inform our searches for life now. And so it's like, okay, so what can we do to get to the end goal? And then even at the end goal, like we will have more questions. That's one of the things that also I've found is that the more answers we find, the more questions we have. And that is just one of the things that keeps me going, or just the more questions I have. And then sometimes I'll just like lay awake at night and I'll just like have an idea come to me. And I'm like, oh, I can't wait to get up and try that and like test out my hypothesis. And sometimes it works out, sometimes it doesn't. And when it doesn't, it's not too discouraging, actually. It's just part of it. And sometimes those will even spur new ideas. So it's just like a self-perpetuating machine.
That's how science works.
Yeah.
Keep questioning. So what's a typical day look like for you? Graduate student, and you're also affiliated with Lowell Observatory here. So do you have a typical day?
Yeah. So as the current stage in my graduate career is the stage where I don't have to take classes anymore. And so earlier, maybe like the first 2 to 3 years, I would take classes on like planetary systems and formation and how that might come about. And so that really lays the groundwork for what I do now, which is I'm done with classes, but I still get research credit. And so I will wake up and I will, I mean, honestly, just like get on my computer and get going, but with some caffeine helps, or powered by coffee. But in all seriousness, it really is there is a lot of coding involved. So I write a lot of coding or scripts in Python to help do some analysis on what I'm doing. So there's a lot of statistics knowledge that I learn. And some of it I actually haven't even learned in my classes. And that requires me to have some like self-directed learning there. So like where can I go? Who do I talk to learn more about Bayesian analysis or something like that? That's just a way to calculate more informed probabilities. And so a lot of it is teaching myself things. And lately I've been working from home and I have my guinea pigs there who cheer me on. And so I'll go over and I'll say hi to my guinea pigs and I'll ask them questions like, so what do you think about this result that I found? And, they just look at me and say, can I have a carrot? But,
and what are their names? Do they have nerd names or?
One is Hero and it's spelled Hiro, Hero. And then one is Pasta and they're really sweet. They keep me company.
So you're a year away from your PhD.
Yes.
You're saying that you said that with a little hesitancy.
Yeah.
Let's try. You're a year away from your PhD.
I am.
Yeah, that's a little more confident.
It's crazy because it's been such a long journey that it doesn't feel real yet, but it like does at the same time.
Yeah. Well, now, I mean, you have the benefit of experience. And so now you're a mentor to, younger kids. And so looking back, when you were 5 or 7, that's a golden age, 7, 8 years old, you get really interested in stuff. What advice do you have for kids that age, with your experience of having, been inspired to do this, you went into it, got an undergraduate, working on the PhD, caffeining your way through it. I mean, what kind of things in school should you pay attention to, or, just in general?
I would say that you don't have to be good at math to be good at science. Science, I think Carl Sagan said this, science is a way of thinking more than it is a body of knowledge. And just keep wondering, keep asking questions. And it's normal if there are times where you may doubt yourself and your abilities, because this is something that can be very difficult. And, but you can do it. You really can. There have been many times where I've had to remind myself, I can do it. And
the guinea pigs
will just cheer me on. Yeah. As long as I give them carrots, that's the thing.
Yeah. That's an easy one. Yeah. No matter what questions you're asking, that's a certain thing. Give them carrots, they'll be happy. Yeah. So we got another question here, it looks like. When you finish your PhD, what's your dream job?
Well, I'm currently applying for postdoctoral positions. And so I get to work at another institution with another mentor on a project that I design. And that's my dream next step. And just continue down the academic path. I really, having the ability to design my research and be at the forefront of human knowledge, I think, is really what I aspire to continue doing.
Yeah. You didn't say anything about Lowell Observatory there. Like your dream job would be to be at Lowell forever, right?
Honestly. Yeah. Yeah, it is encouraged during this stage in my career to expand out and form collaborations at multiple institutions. But I really am thankful and eternally grateful for the support that Lowell Observatory has provided me, and the resources as well. It's everyone here really is a family.
Yeah, it really is that atmosphere. And it's neat. I've been here long enough to see students come through, but then later on get postdocs and get a full-time position somewhere. And somewhere down the road, you're collaborating back with Lowell people or NAU people. And it's really a community. And that leads to another question. The partnerships that you form. You were talking about your team. When you're an astronomer, I mean, there are some astronomers still that work alone and do their own thing, but in general, it's more of a team-oriented thing. Maybe you could talk about that a little bit and how your team, here both at NAU and at Lowell Observatory, how your teams collaborate together.
Oh, totally. Yeah. So a large part of what we do is collaborative. Everybody has a unique set of skills and knowledge and backgrounds. And so one person might have a really deep understanding of like star clusters. And if they joined our group, we could discuss how our topics of interest intersect and what skills can we use to bring together to learn something that only we can do, because we have that knowledge and background that no one else does. And so that makes every team member valuable in our research endeavors. Yeah.
And let's talk about data a little bit. We have one of our viewers asking about the kind of data science that you use, because it's certainly a lot different than what's behind us, how they both look for it, collect it, and then analyze it. So maybe you can talk about that a little bit.
So a lot of the data science that I've had experience using and that I've seen used also is building models, like fitting models to observations. And so this can be done using like Markov chain Monte Carlo algorithms, which are just, it's just a way to throw out like random pieces of information sort of, And then depending on how well it describes the situation that we're trying to model, then it will head toward the right answer or an answer that best fits what we're seeing. And so that's one technique that is used commonly in terms of like data science. I have not used machine learning in my research, but that has become an extremely useful tool in astronomy in general, because we are in an age of human history, I think, where we are amassing so much data. And there are even some next generation telescopes that will come online, like the LSST. That's going to require data science to the point where we'll probably be utilizing techniques that we haven't even thought of yet. Yeah, that's just a few.
Uh-huh. And it brings up something, because we're celebrating National Astronomy Day, and really, one of the key things we do here at the observatory is make space accessible for everybody. So from the beginning, we carry out cutting edge research, but we also make it accessible and fun for people, where you can come up and look through telescopes. So it's neat, because you're kind of the typical Lowell person, where you're real excited about your research and can start nerding out. But on the other hand, you don't have to do that to appreciate the night sky. I mean, what do you do besides, when you're looking at the numbers and everything? What else do you like about astronomy that's just, you don't need any training or anything? Anybody can do it.
Mm-hmm. Yes, that is so true. I love that I can, especially in Flagstaff, I love that I can go outside, and we're in a dark sky town, right? The lights here are designed for the ability for astronomers to see the night sky better. And so I like that I can go outside and then remind myself that the data I'm seeing on the screen is very real, and I am as much a part of it as it is of me. And it gives me more human context, like where I exist in the universe, and my family and friends and the world, and how does this fit? And I think that's what I like about it, is that I can go out and I can look up and say, right, this is where I am, this is where we are. And that's something anyone can do.
Yeah, it's available to anybody. You don't need any special equipment. You can look up, and even if you can't look up, there are other ways of enjoying the universe around us. And yet you're somebody who not only enjoys it, but are helping us understand this. So people that are watching down the road, as they learn more about space, it's because of you and your colleagues. And so it's really enjoyable for us here at the observatory, to have that mission of sharing discovery and sharing the excitement of the universe. And that means you going to science conferences and revealing your latest finds or this new method for detecting exoplanets. It's also you've probably talked to some school groups, or have you done any teaching as part of your undergraduate or graduate work?
Mm-hmm. Yeah, so I've been a teaching assistant early in my graduate years, and that was so much fun. Uh-huh. I loved it. Yeah, it was great.
We have another question from David Moore about the James Webb telescope, and David asked if it ever launches, and I think that's what a lot of us ask, but it seems like it's really going to happen here. Would James Webb, would you use that in your studies?
I absolutely could. So the James Webb Space Telescope will probably initially be pretty oversubscribed. So like what we have to do is apply for time on these telescopes, and then there's only so much time, and it really kind of makes you aware of like human timescales too. You're like, oh, but I only have this much time to answer these many questions. And so really it just requires a lot of persistence, and then you will get some space, you will get time. And so when we do, I would really like to look at these disks even more, I guess. Like that's like, it just, you have more photons with that aperture of telescope, and it's in space. So it's going to be great for imaging, especially like direct imaging of planets, I think would be really cool. I don't have experience in that, but I mean, I'm young, maybe I will. Yeah, that'd be great.
And you bring up something that's really important with astronomy is, as an astronomer, to use a telescope somewhere, you're competing with other people. And there's only so much time on a telescope to look at the sky. And that's one of the benefits here at the observatory. While some of our astronomers, like you said, use different telescopes around the world, we also own our own suite, including the Lowell Discovery Telescope. And so that gives us the flexibility to, especially if there's something really cool happening, we can reposition and look at it pretty quickly, where other places, the telescope's already subscribed. And so that's the benefit we have here, the flexibility of having our own telescopes. Have you used the LDT?
I have, yes.
And what instruments and what were you doing with that?
I used LMI, which is an imager. We were actually taking measurements of planet transits. So that's, like I said previously, when the planet passes in front of the star, the brightness of the system will get dimmer while the planet is in front. And so we were looking at those transits in multiple different wavelengths, because the atmosphere of a planet will, depending on what it's made of, it might absorb in one wavelength of light and not in another. And so if we see that dip in brightness is different for one wavelength versus another, we can say, oh, well, it might have this molecule in the atmosphere. And so that's one type of science that we've done with the LDT. We've also taken spectra using Express, which is a really cool instrument to get really high precision radial velocities. And so this is what it's used for often. That's when the star will wobble under the gravitational influence of a planet that would be orbiting around it. And that planet doesn't have to transit, like the science I was talking about previously.
And Express is a good example of, again, the partnerships in astronomy, both among people and institutions, because Express is the spectrograph that was built by Yale, and there are partners on this. So maybe you can talk about Express, the larger picture of why it was built and what they're looking for with it. I mean, not, well, you, but others like Deborah Fisher and our team with Joe Llama you mentioned.
Mm-hmm. Yeah, so Express, the primary goal is to be able to detect that wobble down to, I think it's like a centimeter per second change in the star's wobble. Because the reason we want to detect it so precisely down, like all the very faint wobble, is because the mass of the orbiting planet really dominates how much it's going to wobble. And so if we're going to look for Earth-like planets, they're not going to be as massive as, say, like a Jupiter. And so we find a lot of Jupiters because it's so easy to detect that wobble, but we haven't found a lot of Earths that way. And so this instrument is designed to say, okay, how small of a change in that star's wobble can we detect? But can we optimize that? Because the more we can do that, the more likely we are that we can detect a planet like Earth around a sun-like star.
So when this was being built over the last few years, you must have been giddy. Like, come on, let's hurry up, get this thing done.
Yeah, absolutely.
It really revolutionizes how we're searching and what we expect to find. And you're on the cutting edge of it. So that must be just really neat to be at a place where that's all happening and you get to use it too. That's just really neat.
Yeah, and you can use it for science beyond just radial velocity observations of wobbling stars. I've also used it to test our ability to detect prominences on young stars. And so the sun also has prominences. If you came up to Lowell Observatory during the day, there might be a telescope out that's looking at the sun. It has to have a filter on it, of course, because you don't ever want to look at the sun with or without a telescope. But you will see these like, they kind of look like hairs on our sun that are coming out of the side, and those are prominences. And it's just like a lot of hot gas that's being shot out on the magnetic field, and it just kind of hangs there. And so these also exist on young stars, but they're way bigger. Like these prominences will extend out several times, like the radius of the star, I think, and they'll hold colder gas out on the edge. And so we can also look for that signature in spectra, and that's what I used Express for also.
Yeah, so a lot of different things you can do with it. Mm-hmm. That looks like we have a couple more questions here. One, David Moore. Oh, David is mentioning about Charles Capon at Lowell Observatory. Chick Capon, he was, I think he was a student of Clyde Tombaugh's, in fact, at New Mexico State University. And we're, the top several rows here are Clyde Tombaugh's handiwork. But Chick Capon was here at the observatory in the 1970s. And we have this classic picture of him that, well, if I go back a little bit, the iconic image of Lowell Observatory is Percival sitting at the telescope.
Oh, yes. Mm-hmm.
Chick Capon, I never met him. I haven't met him, but he used to do tours here in addition to research. And he would dress up as Percival Lowell. And we have a picture of him sitting on the chair at the same angle with his cap turned backwards, just like Percival Lowell did. So by my understanding, he was quite the educator. And just like, what you're showing us here, somebody interested in doing the science, but also sharing your excitement with people. Mm-hmm. Because just like that, our founder, Percival Lowell, essentially said, we want to do science, but what's the point if you don't share it and make it accessible to people? And that's what we do here. And it's an institutional philosophy and also an individual philosophy. But it's really satisfying, when you see visitors coming here and looking through a telescope for the first time, or seeing a shooting star, or listening to you explain how planets form, or any number of things. And it's really satisfying. So it's just Chick Capon was certainly one of those people that really captured that excitement, I think. And we have a question from Christy Engel. Have you published your findings? And if so, where can people find those?
I have published my findings, and until recently, there hasn't been as much discussion about how to make published works available to anybody, but that is changing. Recently, the AAS has announced, that's the American Astronomical Society, they have announced that their journals will become open source soon, meaning that anyone can read the publications in their journals. Until then, I'm not exactly sure the timeline in which that will go through, but until then, a lot of researchers will post their works to an online site called Archive, which is also open source, and it's ARXIV. And you can, it's not just astronomy, there's actually a lot of really cool science that's published there that anyone can access. And I would say go there for now, at least until the AAS journals become open source.
And that's really changing everything. I mean, well, just like everything used to be printed, now, more and more is digital. Eventually, all research is going to be digital. Libraries are one things that they're not growing that much now because, journals are going to digital. It just changes how we do a lot of things. But it's nice to be able to have that accessible.
Yes.
I know for my part, sometimes, writing about a discovery and wanting to see the paper, but you can see the abstract, but then you have to subscribe. Mm-hmm. But to be able to see it, the entire paper, and a lot of science papers, the a typical person not doing astronomy may not last more than a couple sentences to where, they find something a little, maybe more interesting with all the numbers and stuff. But on the other hand, I don't know, every paper that I've seen, you get something out of, even if you don't have a background, you get the gist, so I summarized what was the important finding here. And even if you don't read everything, just scanning, the results can be really informative and exciting to see just the diversity of what's happening. Let's see, we've got another question here. Again, from David, is there anything amateur astronomers can do to assist your studies, assuming proper telescope size?
Oh, I do know that some amateur astronomers have collaborated with professional astronomers. There's actually one that is in communication with someone in my group, and so it is possible. It just takes some reaching out, but also anyone can become involved in astronomy research with citizen science projects. Those exist online, and like there's one called Galaxy Zoo, where anyone can go on and help classify galaxies. There's also like a lot of classifications that you can do for like solar data, like what type of spot is this, and like where does that fit into the context of solar physics? And it's not uncommon, actually, for every once in a while, someone will come across, a citizen will come across something really interesting, and that will be flagged up to the people in charge of the citizen science project. And that citizen could even become a co-author. It's not unheard of, at least.
And we've certainly had some amateur astronomers helping with research. Gerard Van Bell had one of our astronomers here. I think he still has some amateur astronomers he works with. And throughout time, we had a program at one point. And so, a lot of amateurs, it's neat when you go to a major star party, there are some major league telescopes that amateurs have bought. And it's amazing. You don't always need the Hubble Space Telescope or the James Webb soon to make so many fundamental discoveries. Georgy Mandashev, who was just in here a little bit ago, he was involved with the TRACE program looking for planets. And using, I think it was a 4-inch diameter telescope, they discovered one of the largest, if not the largest known planet on record as of right now. That will change. But it's the equipment, it's the people, the techniques. There's a lot of different things that go into doing research or even just looking at the sky. Mm-hmm. And so you don't have to have the Cadillac necessarily to do a lot of that. So we have another question here. If politics, political borders, money, resources, if none of that was an issue, what would be like the coolest, the most important instrument or equipment to do astronomy? Money's no object.
Oh, that would be so cool. Okay, so I'm not sure if I'm answering the question necessarily, because it made me think of what's my dream telescope. Mm-hmm. So I'll address the question first, and then I'll tell you what my dream telescope is. So I think the field of astronomy, like as a whole, would really, would really benefit from having more facilities, really observational facilities. I was saying earlier that we have to apply for time to do our science on many telescopes, and we've had to compete with other astronomers for that time. And so I think that wouldn't be as much of an issue if we just had more large-scale, next generation observing facilities. And
so what's your dream telescope?
So my dream telescope is a very large interferometer that exists in space. And so an interferometer is a telescope well, it counts as, it's like one telescope, but really there are multiple telescopes really far apart from each other, and then they can combine to form an image. And what it allows for is extremely high resolution images. So when we, doesn't matter right now, the telescopes that we have, no matter what the star actually looks like, to us, it's still going to look like a point source. But if we had a large enough interferometer with a long enough baseline, so that's the distance between the individual telescopes that would make them combine to form the image, I think that we would be able to actually image stars and their surfaces and star forming systems like my group researches with very high resolution, and that would be so revolutionary. That would answer so many questions that we have. Yes.
So. And maybe you can talk a little bit about Lowell's interferometer and what's being done with that. The one that's not in space but is here in Flagstaff. I know you don't use that, or you've never done any research with that, right?
I have not. I'm actually not as familiar with that.
Okay.
With that facility.
Well, it's like you were describing an optical interferometer with dishes spread out over several hundred yards, and we'll be expanding that to where it'll be the largest one in the world. And Gerard Van Bell is heading that project, but it allows you, like you were saying, the resolution. You have to look at bright objects because it's not like you have one big mirror. It's a bunch of smaller ones, but they're spread out, so you can see an object from a lot of different angles to get good resolution. But they have to be pretty bright to be able to see it.
Yeah, and I do know that it is more difficult to do in the optical. So like what I mean by the optical or visible wavelengths, light that our eyes can see. And I think those are the wavelengths that interferometer combines.
Yeah, that's it's called the Navy Precision Optical Interferometer. So we work with the Naval Observatory and the Office of Naval Research. It's a big partnership, and it's a magnificent instrument. When you see it, how it works and everything, using vacuum tubes to send light photons back and forth, it's really a high tech thing. But it's neat because it's located, out at Anderson Mesa, our dark sky site across from Lake Mary, and the Arizona Trail is nearby. So you can walk by, and it's fenced off, but you can still look and see this really weird array on this Y-shaped pattern. It's really neat to see. Kind of like the LDT, the Lowell Discovery Telescope. You drive down Lake Mary Road, and suddenly there's this big, flying saucer-looking thing in the middle of the woods. And it's this 14-foot diameter, 4.3 meter telescope, and its dome that are out there. And it's out there because it's dark, and the seeing conditions are good. So let's see. The statement, how you answered it was just what they're looking for, kind of a reach for the star side of if you could have everything. Now it does bring up something I think is interesting. We have people that are going back into space, and we've had astronauts going into space, but commercialization is redefining what it means to go to space. And it'll be interesting to see what impact that has on science as private companies work with NASA to go to the moon and elsewhere. But that costs money. The privatization is one thing, but for a long time there's been an argument. If NASA, for instance, has only so much money, is it better to send people into space, or for a lot less money, and you could do a lot more in some ways, to send unmanned or uncrewed craft into space, or don't send any craft and just use the telescopes we have here and bolster them? I mean, what do you think about all those? Is there a better solution, or how we should spend that kind of money?
I think yes to all that. Yeah. I think that any way that we can do it, we should.
Mhm.
And whether it's privatized or not, I'm optimistic for humanity's progress
Yeah.
in exploring the cosmos in a physical sense. And so I am, no matter how it is done, I am all for it.
Yeah. And there's something, because as human beings, we're inquisitive, just like you've been all your life, asking questions, and to be able to send our species to another world. I mean, the technology we got out of going to the moon, all the spin-offs, and from medicine to microwaves to our watches and cameras, the way we live today is a product of the space race. Mm. But even without that, sending a human, our species, somewhere and describing what the universe looks like. I mean, there's that human part of it. And even though you're not going into space, at least yet that we know of, I mean, your ability to share the research, that's what inspires people. That's what makes it. You can look at numbers and you can look at results, but when you hear how people did it, or you hear about like the old days of like Clyde Tombaugh sitting in the cold telescope dome, it could be 10 degrees inside there, looking through this eyepiece for an hour, trying not to fall asleep, and then developing those images, looking through this machine called a blink imperator, where he spent a total of 7,000 hours of his life looking through this eyepiece at millions of dots. That's hard to grasp, but when you hear somebody describing it, what it takes to do science, it really makes it a lot more fun, I think. And so there's that value of the human experience also. Mm-hmm. So, like in your experience, what's been your like coolest astronomy moment? I mean, is it that like the results of a paper, or looking through a telescope when you were 8, or what is there one thing that just really jumps out as the coolest thing?
Yeah, so it's going to be a tie between the moment where I actually was in Florida with my papa, looking through the first telescope that I'd ever had.
How old do you figure you were?
I must have been 8 or 9.
Mm-hmm.
Yeah, and that was particularly magical because it really made the universe bigger for me.
Yeah.
I realized, there's a lot more out there. I'm like actually seeing this object with my eyes, not just like a picture of it, It's still, I think those are still beautiful and extremely inspiring. When you see them with your eyes, it's like there's much more of a connection with it, I would say. Mm-hmm. And then my other favorite was when I was an undergrad at the University of Arizona. It was my very first observing run. I went with the astronomer Betsy Green. She took undergrads up to Mount Bigelow 61-inch telescope, and we observed all night. It was a binary system. We were looking at just like planets transit stars, other stars and binary systems can also pass in front of other stars. And so that's what we were observing, just that change in brightness from 2 different stars orbiting each other. And we didn't sleep all night. Mm-hmm. We stayed up all night, and I was so tired, but we got to watch the sunrise. And we had the most beautiful view. And I remember that was when I was thinking to myself, like, I knew I wanted to be an astronomer. I was in the program, and I was, doing the thing, doing my homework, going to class. But in that moment, I realized, I can do this. I could do this for the rest of my life. This is what I want. This is it. So I think that's the other moment.
Magical.
Yeah.
And, it seems like just about everybody you talk to, it doesn't have to be science, but people who've really followed their passion, there was something that fired them. Phil Massey, one of the scientists here, he went to just about all, if not all, of the Apollo launches, sending humans into space. And that really inspired him. And some of our other scientists, it seems like, my interest in science goes to 7 years old, picking up a fossil, thinking, Mike, look at this thing. And it just captures you. And it's that magical age, it seems like, I don't know, 7, 8, 9 years old, where you're just, the universe is yours.
Yeah, you're brand new in it, you know, you want to take it all in.
And it's interesting because you said, you know, what those two things, one of them was looking through the eyepiece of a telescope with Papa, and the other was looking probably at a computer screen at graphs of the brightness. Is that right?
Yeah, all night. That's what we were looking at. We actually didn't even look through the eyepiece at all.
And yet that's still because you realize what that means. Because it's not just looking at numbers or a graph, but it's what you're learning from it. Mm-hmm. And that, I think that's an important thing, because a lot of times there's this idea of science, you know, staring at computers, looking at a bunch of numbers, but it's what's behind the numbers. Mm-hmm. And that's what you do, is interpret it and then explain that to non-experts of what it all means.
It's still very meaningful.
Yeah. Well, it looks like we have about 5 more minutes. So, and I think we have a couple more questions. I'm kind of following up on your discussion about your dream instrument, the interferometer in space. The question is, could you put telescopes or some sort of sensors on planets, the moon, and triangulate and have a, you know, I mean, that's kind of like a big interferometry system.
Yeah. I think if we put them on different bodies, that might make it difficult, because those would be moving constantly relative to one another. I've never considered something like that, and I wouldn't write it off necessarily, but it would definitely take some more thought. Some more thought and some more time to think about it than I think that we have. But that's an interesting idea.
Yeah, and you know, it's amazing how far we've come, because I know Gerard Van Bell a couple of years ago was working on a proposal to do 3D printing in space.
Yes, I was actually at a conference where he gave a talk on that, and the idea of building a telescope in space really helps with when you make it in space. You don't have to send the whole thing up at once. It's not as heavy. And then it also allows you to do some things that you wouldn't have been able to do here and then get it up there. That's just like the right away benefit to that. But also, when I was talking about like my dream telescope, that like wide interferometer, his proposed instrument would actually allow us to image the young star systems that we look at. And so I'm all for it. I'm behind it 100%.
And it's only a matter of time. I mean, we start getting these ideas, like all science, you get an idea, and sometimes it takes a little time to develop it and the technology, but you know, 3D printing is changing how we do a lot of things. And to think you can build, you know, instead of assembling it here and then getting it up there, building it in space, it's hard to imagine, and yet that's going to happen. It's so neat. Well, we've got just a couple minutes left here. So let's go through the last comments. And if anybody has any final questions for the future Dr. Biddle, write those in the next couple of minutes. David, you're going to be visiting Flagstaff. So I'd love to talk to you. I'm kevin@lowell.edu, my email, kevin@lowell.edu. So get a hold of me, and we'd be glad to talk to you, look at some pictures and everything. So we've got just a couple minutes left. So let's see, I don't know, 35, 40 years from now, you're going to be thinking about retiring maybe. And as you look back on your career, what do you want, you know, what will you say was a successful career for you?
Oh, that is, never thought about that question. What would make my career successful to me? It is one where I am able to contribute to the body of knowledge of humankind and connect with people like you and share my science and get it out there that astronomy really is something that is for everyone, and that you can do it. And yeah, I just want to share what I've learned, and to anyone who will listen, really.
Well, that's great. And that's, we should always all leave the world, or here at Lowell, we talk on larger scales. So the universe, we should all strive to leave the universe in a better place. And to get people excited about learning and about the universe around them is a real noble goal. So we'll look forward to following your progress on that.
Thank you.
So thanks so much for joining us tonight.
Thanks for having me. This was a lot of fun.
And thank you, everybody, for joining us. Thanks, Danielle and Maddie and Heather. And I hope I didn't miss anybody. But thanks for the behind the scenes making all this work. And we'll see you next time. Thank you.